is actually directing not visible light, but the same thing as light. So if you see things reflecting in mirrors, when you see a laser, all these sorts of things is actually what you're doing with a conductor, but at different frequencies. But it's still the same sort of form of energy. It just turns out that we have electrons which have charges, which make electric fields. And electric fields, when you have an electromagnetic wave, you can imagine that they'll interact with each other. So if you have like a conductor, which is just basically something where charges can move around freely, if you have a wave that it interacts with this, you can kind of confine it. Okay, so that's what we do. That's what a transmission line is. You're confining electromagnetic waves. Remember that electric and magnetic waves, they're very linked to each other. You'll see with Maxwell's equations, when you change the one, you make the other. You've seen with Faraday's law and like all these sorts of things, that they're very, very related. Okay, so basically we're conducting electromagnetic waves. There's like an electric wave like this. There's kind of perpendicular to this. There'll be sort of a magnetic field where a field is basically just a space that has some sort of quantity in it. Can be a vector, can be whatever you want. So we're just kind of confining that. Okay. So if you were to look at this sort of structure, like let's say a two-wire sort of structure, where there's a current going and a current returning, actually there's a linkage between these two things. Okay. There's two types of linkage. There's a kind of a magnetic linkage between each piece and a capacitive sort of linkage between each of them. Okay, so if you had like, so if there's little charges that are being like compressed or expanded by the electric field, which is kind of like your wave, a squishing of those charges, so this is like one form of those energies, of this wave propagating, we like jiggling around these electrons, you would see that actually the amount that these compress, so on the one side it will compress, let's do that actually in blue, let's say this side it compresses, so it becomes negative, the electric field is going to be stronger here, then over here, or there'll be a difference, this will be like kind of positive, and these actual charges are interacting with each other between the two of them. So this is kind of an electric field, and then that compression wave, you can kind of see it as like, okay, there's a compression wave, and then that's going to travel, that's sort of jiggling down these wires. So we're confining the field to between these sorts of things. So this is the traveling wave. There's an interaction. Can you actually see my mouse on where I'm pointing?
Yes, we can.
Okay, so then there's an interaction between the two wires, which is an electric field, which is kind of exactly what a capacitor does. If you have two conductors like this, can you see that a capacitor is a storage of electrons? So on the one side, it will become like, let's say, like very negative. And then on the other side, this will repel away the electrons. Let's say they go away. So then this side will become positive. So you're negative. So that's sort of in a transmission line. And that's what this capacitor describes. That sort of behavior. It's kind of a starship. When the electrons are moving, they'll kind of make a magnetic field that opposes it. And the degree to which that happens is kind of governed by an inductance. Okay. Then we also have a loss. Wait, sorry, there's lots of people being noisy and calling dogs. We have a loss, just normal losses of conductors. When electrons are traveling, they kind of encounter resistance and dissipate heat like this. Some heat's coming off. That's what this resistor kind of signifies. And then there's this sort of conductance, which is this conductance with the G, okay, which is kind of like if you have a dielectric. I guess now a dielectric is just something that separates. It's like a insulated in a way. So it's the opposite of a conductor, but it actually polarizes. So it becomes positive and negative. So like it becomes positive and negative, and that has an effect on the electric field. Now, if your dielectric's not perfect, what will actually happen is that you'll get a loss with the electric field as it travels. Okay, so if you look at like should I get a photo of an actual transmission line? Maybe I should do that. Let me get an actual photo and you'll see. You'll see, okay, well, no, we don't even need to, I don't even get a photo. If you see even in your normal, like, twisted cables, like a earphone or whatever, we have the twisted cables, you'll see there's kind of stuff in between it. That's kind of a dielectric. But in power cables, it's way more prominent. Okay, now when that electric field is going through that dielectric, there can be a loss. In a similar way, when a current is flowing through a conductor, you can get a loss to this dielectric. So that's what this conductance represents, a dissipation. All resistive elements represent a dissipation of energy, and a specific dissipation that allows for the voltage and current to stay at a certain ratio. That's kind of how it does it. It dissipates, and then that's how you enforce that sort of ratio. So that's all of the components describe what they all do in this equivalent circuit, and what they're actually describing is an actual little slice, a slice of this. So if you take out a little slither, an infinitesimally small piece, okay, if you take that out, okay, you get the one piece of this transmission line of this equivalent circuit. Then you get that whole thing with the two the inductors, and then there is the conductance and the capacitance. I'm drawing it very badly, but you get all of that. And then if you're to go one little infinitesimal more to the right, so we're going to just call this x, okay, so then we'll call this dx, you get another one. Okay, so you get another resistive element, you get an inductor, you get conductance, you get a capacitor. Okay, and then that keeps on happening. Infinite, you'd have to integrate this whole thing over length. Okay, and then that's what this equivalent circuit is kind of representing, is a piece of that line. So let me just slow down because I've said a whole lot of things really quickly here. Are we all okay with the concepts of what these things are, the circuit is representing? Can we see that it's also a length, not a length, an infinitesimal length? So when I say R dash, that means the resistance So it's like a metric that you give to a transmission line. So if your transmission line is 10 meters long, and you say that the R dash is like, let's say, 10 ohms per meter, then your total resistance of the actual transmission line will be 100 ohms. So when you, in the equivalent circuit, you're actually dealing with the per length measurement. Okay. So that's the infinitesimal thing. Okay, so now when you integrate this thing, when you piece lots of them together, basically in normal circuits we have no understanding of spatial dimension. We don't explain anything over space. There's no propagation speed. We do, however, have these amazing things. Okay, we have V is equal to L di dt, and we have I is equal to C dv dt. And with these, which is the equations for an inductor and for a capacitor, these sort of equations give us a time relationship. Okay, so if you had just had a normal resistive circuit like a voltage source and a resistor, you'd notice that your voltage or your current over time would actually, so if this is voltage and this is resistance, and this is like our voltage source, okay? If we're to graph our voltage over time, here's our axis time, and here's voltage, you'd actually see that it would stay a constant height. Okay, it wouldn't change. But if we actually have, instead of a resistor, if we have instead a capacitor, Okay, well, let's just put a resistor with it because then you get like a little RC circuit. And you solve the differential equation. So it'll be for this one here. You'll actually get some sort of, let's draw voltage. What's actually going to happen is that it's going to store voltage. So it's going to do something like this. It's going to go to store it, to like increase, and then the current will do like kind of the reverse. It's like the reverse sort of thing. That'll be the current. So in time, current and voltage change because of these derivatives. But there's no understanding of distance. There's no length. There's no propagation speed, but there is a time, a transient behavior. But now by explaining that we have an infinitesimal piece, we can actually integrate that over length. So now we have sort of a length, okay? And we have transient behavior happening along that length. Now suddenly, because things are changing, so they're changing in time and in distance, if this is distance, we actually get a propagation speed. So the propagation, the change of one sort of, at one circuit here, so we have one little small circuit here, the change across here that takes time will then change to the next one that will also take time. It will change to the next one that will take time. And thus we have propagation down this line. So that's the whole point of this section, is to explain of circuits where there's no propagation speed, we assume it to be instantaneous. It's one of the assumptions of circuit theory, because circuit theory is actually an approximation, even though you've never considered it, but it's a very useful approximation where you just say that things bounce around and become stable. Now we're actually going to say that things take time to travel. And that's what this reflection diagram that you've been seeing is actually explaining, the transient behavior. You will not get that from circuit theory by itself if you just draw without considering that sort of traveling wave, the traveling electromagnetic wave. So that's what this circuit is explaining, a speed. And you'll see that these speeds are very related to these parameters of inductance and capacitance, which is what we'll get to next. Let's first just say, take this lossy sort of thing where we have losses of the G and the losses of the R, these heat losses. Let's make it lossless. How do we make it lossless? Value must I give to R prime? Okay, R prime meaning the resistance per length. Remember, it has to be per length because it's the infinitesimal piece. It's not the total resistance of the whole transmission line. It's the per length resistance. What must that be to make this lossless? How many
0.
ohms per meter?
Is it 0?
0. I heard your voice is very, very soft. I
I'll
don't
try
know
to talk
if
louder. Is this better?
you're super duper soft. I don't know if it's just you, if it's maybe wait, maybe
It's
I
not
turned it
soft for
down.
me.
Wait, I
I
also turned.
can hear him clearly.
It was my headphones. I
Okay.
think in my explanations I like knocked my volume of my headphones. So you said 0, which is correct. Okay, and then what value for conductance? Okay, so conductance, this is something you have to be very careful about. If you look at the resistor itself, okay, the resistor, it signifies a dissipation through the sort of the dielectric. But what it's a little bit confusing. So what value must that resistor be? Because the truth is that this is a leakage. You have an insulator in between these two lines, and if a current is flowing, that's a leakage, that's a loss of energy. So what value must G have in ohms? In ohms per meter, does anyone know? If we don't want a loss, so this is the dielectric, we don't want actually a current to flow through it. 0. So no, you would want to say 0 because you're thinking resistor. It's a different sort of thing. It's not actually the dissipation in heat. It's actually the quantity of current that it's doing. So it's kind of the reverse. So it must be infinity. Okay? The reason why it must be infinity is because look at this. If we have a circuit like this, with, let's say, we're just going to do the capacitor and the resistor. Okay? Remember, if current is flowing through this branch, that's considered a loss. That's considered if we have an insulator that the current is actually flowing through it. Yes, you were wrong, but it is such an easy mistake to make. And you'll see actually in the equations that they say, actually, G prime is equal to 0. But what they're actually speaking about is Siemens per meter. Because remember, that's the conductance. Okay? If you go 1 over R, which is, like in the units, 1 over ohm, then you get Siemens. Like that company. So then that must go to 0. The conductance must go to 0. Okay, the actual value, if they ask what is the value in ohms, it must go to infinity. The reason why is because if it's infinity, what do we have? We have an open circuit. Nothing can flow. There can be no loss. You want energy to propagate down the line, not like through the dielectric. It's just a symbol, so it's not the classical sort of resistor that you use on your board, but it's that sort of concept. Okay, so that's something I really wanted to point out, so you guys don't get confused. If they're asking ohm, infinity. If they ask for Siemens, 0 to make it lossless. Does that make sense? That means we get left with this. We just get our time variation components for a lossless one. There's no loss. Then we just have a C per meter, well, per length, and then an inductance per length. And this is our lossless transmission line. Okay, so there we go. That was the start. That's how you get your lossless one, and that's kind of but I don't continue explaining, but it's already like quarter to, but we haven't even started. But quickly, sorry, I'm babbling, but is there any questions on this? I'm going to briefly pause for you guys to ask. Let's see. Okay. Are we in understanding? I'm going to assume understanding. Quickly ask. Okay. So there we go. Now, we're going to look at our equations that we're going to start with characteristic impedance, which they give with a Z. Okay, they say in a transmission line. Okay, let's give this a context. Did you see over here that there was a sort of squishiness? How much capacitance you had, and then there was kind of a resistance with the magnetic field time delay with the inductance. Those two things, inductance and capacitors, combine variation over the distance. Remember, this is dx. With these things, can you see that they kind of each saying like voltage, one saying voltage, one saying current, and then they're kind of the derivatives of the other. If you go down the path of actually looking at this and deriving like they do in the slides, or if you can check the appendix of my master's, you'll see that this makes in a wave equation, okay, which kind of shows that the change in the one kind of creates this sort of disturbance that can propagate when you integrate it over the distance. But that change is very dependent on how large these variables are. Okay, so between the two of them, there'll be kind of a bias towards maybe a higher voltage ratio than current ratio. And it turns out that there is actually a constant ratio. And that ratio is called the impedance. and we call it the characteristic impedance. Here I've just put in a 0. You can have Z1 if you want, if there's multiple transition lines, Z2, but the main thing is that this is an impedance that is describing the ratio of voltage and current, the same way you've seen with a resistor has an impedance, okay, also in ohms. So this is actually measured in ohms. Now, if you do that, there's a bunch of derivations around this, but this one's a bit of a tricky one that you can't show very easily. This one's equal to the square root of inductance per length over capacitance per length. Okay, and that kind of, the way you can kind of see it vaguely is that you can see that voltage is kind of the inductance, and current is kind of the capacitance over here. So then if you see voltage and capacitance over here, I mean voltage and current, you can see there's kind of like voltage and inductance. You can kind of remember it like that. It's not very rigorous, that explanation. There's not really a whole logical thing around that, but yeah, that's the kind of idea. Why the square root? You have to do the derivation to get the square root. I can't easily show that or even explain it to you very easily. But this is the formula. Okay, the characteristic of how things flow. Characteristic impedance or surge impedance. This can also be called surge. The surge impedance of the line. You might see that written. That's one formula you would have seen. The next formula is the actual propagation speed, which is what you get from that wave equation derivation. There's that general equation, and there's kind of like the c squared term. You'll have like the second space derivative, and then you'll have like the second time derivative, and this can just be like whatever function if it's a wave equation, and then you'll have this c, okay? And we actually work it out. It comes to this. I'm going to say VP, which stands for like phase velocity, or the propagation velocity, okay? And that's equal to the square root of 1 over LC. Okay, cool. So it makes sense. The ratio of voltage and current was governed by an inductance and a capacitance. Now, the speed at which something travels is also governed by those two parameters. So this is also for the lossless case. In the lossy case, it's slightly different. This is because, remember, this is the only two things that are actually describing our transmission line. But it's the per length. So there we go. This is actually your thing. Someone's mic is going. I can just hear crumbling. Talenta, is that how you say your name? Your mic is on. I don't know if you know.
You might be able to manually
I
mute
can.
participants.
Well, I can. That's cool. Okay, so that's cool. So that was your phase velocity, which was also dependent on these two parameters, as well as your impedance. The other two parameters, slightly different formulation. So this is velocity, the speed at which a signal will move down the line. Okay, which is also interestingly equal to the speed of light. If you have the speed of light, remember we're dealing with electromagnetic waves. You know that constant c, okay? That's, if you look it up, will be equal to the square root of mu. Okay, we'll say in a vacuum, so it's mu naught and E naught. Okay, and if you actually look up what mu naught, which is permeability, they'll say it's like the inductance of free space per length, which is cool because look, this is an inductance per length, but this is of a vacuum per length, and they'll describe permittivity as the capacitance of free space per length. how much electric field, the smallest quantity that it kind of can contain, and permeability is for the magnetic field. Okay, so that's interesting. So this is actually a very important thing. We're not going to get asked this, but this is just a very important constant in our world with this speed of light of a vacuum. Remember, it's in a vacuum. That's the constant. Speed of light does change. As we can see here, it depends on the inductance and the capacitance of the medium with which it is traveling in. So that explains it here. You can also actually write this formula in terms of, I'm just going to say Vp again. You can say it as 1 over mu r ER, so the relative ones. So then that will take it out of the vacuum. Okay, so these are all the formulas that you've been dealing with. I'd say these two are very important, which I'll label 1 and 2. 1 and 2, those are very important, that you understand them and how they relate. The new one that you've dealt with now is the reflection coefficient. Okay, I'm going to give it that little gamma sort of sign. Not gamma, what's it called? Rho. Or yeah, you'd like to use gamma. And then that's equal to, who knows this? Can someone say this off by hand?
It's the I know. Can I say it?
Yes, please.
It's the impedance of the thing you're going into, or the signal's going into. So the second impedance minus the first impedance over the sum.
Yes. Okay. And I'm going to write it like this in a very ambiguous way, where, and this is what's often referred to, they often call this the load. Oh, can I not undo? Yeah, I can. They call this load, and then they call this kind of Z naught. And that's kind of dealing with if you have a transmission line that's like this. Let's draw it like this, actually. This is typically how they draw a transmission line, this fat piece. Because you can use circuit theory on each side of it where you're not so concerned about how long it takes for things to travel. But you could say, like, yeah, you have like a power station, or maybe even like a CPU, and then you have some other component where you're switching so fast that actually it does matter this time, because you're looking at it in such a fast frequency, gigahertz. Think about what a gigahertz is. I think it's 1,000,000 times per second, a gigahertz, which is absolutely ridiculous. But anyway, they call this, like, if they have this as Z naught, and then they have some sort of a load, which they'll call ZL. Then that's why they normally say they have this L here. That's for the load. And they say Z naught. Z naught is the typical thing that you give for the characteristic impedance. That can be any number. But that's very confusing because that's given that we're traveling in this direction, okay, to a load. You can actually get reflections, as you'll see on that on my course page that I made. You'll see that there's reflections when you go from one string to another, or what you can say from one billion one transmission line to another. So this works for loads because they govern a certain boundary condition on what the ratio of voltage and current must be. That's actually why you get a reflection, because on each side of the line, you need to say that it must meet that ratio. Let's say this has 1Z. We'll say this is Z naught, and we'll call this Z1. You actually need to say that at this point, when a wave approaches, it needs to satisfy both this ratio of V and I and this ratio of V and I on both sides. And then that's actually why you make a negative traveling wave, because it kind of adds up with the forward traveling wave, and then it makes that ratio equal on both sides, so you actually have energy conversion. I mean, energy conservation. So that's what's happening. Where the reflection, if you actually do the computation, you'll see that's actually what it's showing. I think I do that in my master's as well. If anyone needs, it's the appendix. The appendix of the master's is where you must look. It's like has all the derivations. If you need, it's not at all necessary to be tested, but if you feel like you need deeper explanation, I've like kind of compressed it. But here, if we have a wave traveling, back to why this is ambiguous. You see here where they say ZL, but why that can be ambiguous is that, let's say we have a a wave traveling from Z0 to Z1. It gets to Z1 and it will get reflected, okay? The reflection coefficient will equal to Z1, that's where it's going, minus where it came from, Z0, divided by the sum of those two, Z1 plus by Z0. Okay, so that's a fraction. This will be something that's less than 1. Can you see that the difference between two things can never be greater than the sum of those two things? So this thing, it can be 0 and it can be 1 if like one of them is 0. So if like Z0 is 0, then you can get 1. So then you can just say the magnitude of the reflection coefficient is less than or equal to 1. Okay, which means that you're going to get a reflection that's going to be at most the same size as your incident wave. So yeah, can someone give a scenario where you would actually get your whole wave reflected back in a circuit scenario? When would that happen? There's actually two scenarios. One will be inversed. Infinite.
So when Z1 is infinity,
Yeah. Then what is our reflection coefficient if Z1's infinity?
it's 1 because Z0 is negligible.
Well, yes, exactly. And then how do we get -1? Oh, good. I was actually going to say you're wrong, but you're right.
I think you get -1 when there's a short circuit, so your ZL is 0.
Yes. Okay, then you get it. Okay, then it's 0. Then if this is 0, so let me just show that, just so you know. Let's say, okay, that's Z1. We're going to do two scenarios. It's going to be either infinity ohms or it's going to be 0 ohms. So let's draw those scenarios like this. Okay, if it's infinity ohms, then, so if we draw our transmission line, what's going to actually be infinity ohms is basically means you can't go there. If you can't go there, that's pretty much like an open circuit. So if this is Z0, then Z1, this becomes an open circuit like this, because you can't actually go there. So when I draw these thin lines, that's kind of the circuit theory lines, where remember lines just connect nodes. The length means nothing. So here that length actually means nothing. It's only these kind of fat parts where we're saying that we're actually considering the propagation, this significant propagation delay, or something that we want to actually to analyze that. So these little extra lengths don't mean that there's more length there that we're actually calculating. We'll do one for 0 ohms. What is 0 ohms? A perfect conductor, which is also what those little circuit lines do. So that's just something like this. Short circuit. Okay, if we calculate our reflection coefficients for each of those, so here Z1 is equal to infinity, open circuit. Z1 is equal to 0, short circuit. We'll say open circuit. We say where we're going first, okay, which is going to be infinity. And I'm just going to write it at the bottom because it just makes sense so you don't get confused. I just do that. This will always be plus. And where I'm coming from, you minus it. So that'll be Z0. This will be Z0. And then that'll equal to 1 because it's infinity and infinity. This, if you minus a little bit from infinity or plus a little bit to infinity, it's infinity. And if you do the short circuit, this is going to be where we're going, 0 ohms. And then I just do it at the bottom. And then you say where we're coming from, you minus that at the top. And then this is equal to -1 because you just get left with this. Okay? Clear? For those maybe that weren't on that page, now that hope everyone understands the -1 and the +1. Going back to why I carried on saying it was ambiguous. Oh, wonder how I selected that. That this load was ambiguous. When it becomes ambiguous is that actually the reflection coefficient when you approach from this side, can you see? And there's a reflection coefficient when you approach from this side. Oh no, sorry about that. It's my mom, actually. It's her birthday, funnily enough. Where it's ambiguous is like this. Okay, so now let's say we want to just define reflection coefficient overall. Okay, and we could call this ZO, but we're not going to call it ZO, but we could, but we're not going to. Okay, we will. And we'll call this just ZX. Why not? A wave traveling from ZX to ZL will get reflected and go back on ZX, and it will have a reflection coefficient of ZL minus ZX over ZL plus by ZX. Okay, if we have a wave traveling in ZL towards ZX, then we'll get a reflection that comes back along ZL. Okay, so then the reflection coefficient for that will equal to ZX minus ZL, where we going, where we coming from. Then this is ZX, where we going, and this one doesn't matter because it's plus, but I just like to pair them like that so you don't make a mistake. I thought that you say happy birthday. I'm sure she'll be happy. So yeah, so then that's how it's ambiguous. So when they just say load, you don't realize that it must actually signify where you're going. Where you're going. Okay, so make that very clear, you understand that. I was slightly confused about that, but it's very basic. Okay. So, questions so far. Reflection coefficient. Does this make sense? It's a portion that's going to be reflected.
So I have a question, but you might cover it next. Are you going to do an example with this?
Of the reflection, like I promised. Yes. That's
Okay.
exactly what I'm doing this. I'm so sorry. You guys have gone through all of this stuff. You're like, oh my goodness, please can you get to this practical example that you promised? It's already 4 o'clock. What is going on? So let's do it. Let's start with the basic one. Okay, we're going to have a voltage. Okay, we're going to have some sort of input resistance of this source. Okay, so this is a voltage source. This could be perhaps a CPU. This could be a voltage station. Okay, and it will have some sort of impedance associated to it. Let's say we have a switch. Okay, and we connect it to a significantly long electromagnetic conducting structure. Okay, which is a transmission line. So there's going to be a time delay. We can describe how long it will travel based on the per length values. So if I tell you that the whole resistance of the line, I measure from here to here, and I measure that this is 100 ohms, okay, and I tell you that the length is let's say 50 meters, and that would mean that R dash is equal to 100 over 50, and then you would get 2 ohms per meter, not 100 in your calculation. If you want to calculate the speed of propagation, you use per distance, not the total recorded one. Watch out for that, please. Okay, so again, just continue, and we want to see what happens in this sort of system when, let's say, it gets to some sort of load. Okay, and we'll say that this has a characteristic impedance of Z naught. Wait, let me just close my door. Okay. So I told people to not to be speaking. Shame. Okay. So the way I'm actually working now is actually quite a communal space. It's a shame. It's not so fair, but what can I do? Here there's a voltage. Okay, so there's an impedance which is going to have some sort of propagation. That's going to take time. It's going to have a length. This is going to have a length as well. And then we can work everything around there. Okay. What's probably good to start by doing is realizing that a traveling wave will be reflected. And that's going to be told to us by a reflection coefficient. So let's call this reflection, we'll say coming from 0 to load. Okay. Here we'll have a reflection. So this is the one that's it's coming this way. If we draw an arrow that it's the direction that it reflects, let's draw the arrow in which it's coming from, like that. And then there's another one, so I'm just going to get rid of this length, which I'll draw on purpose like this. When it's coming from 0, and now it's going to the input. Okay, so I'm going 0i. Two different reflection coefficients with two different values. Okay, so if we were to just calculate them quickly, 0i, I'm going to leave that open. You guys can type that in the chat. What each of these are, just say reflection. You can say, maybe call this input 1, and we'll call this one the load 1. Just write that for some interaction, and I'll write what you guys write. The first thing that we're going to do, so that's kind of like the first thing. You kind of analyze your reflection coefficients. The next thing you're going to do is the initiation. So here's the switch. We're going to close this switch. What's going to happen? Okay, so this I'm going to call step 1, initiation. Okay, so we're going to also say that this line is discharged. There's no charge on it. It's at 0 volts. There's no electric field currently. There's no currents fluctuating in it. We're going to close the switch. And what is going to happen? Okay, so when we close the switch, now we say we're drawing these wires here because we're saying the propagation is not significant enough. Okay, it's just small. We can just do normal circuit theory. Then it's going to encounter a structure at these two terminals, a structure that is going to enforce a certain ratio of voltage and current in the exact same way that a resistor does. So what circuit theory actually does, all the rules you know as circuit theory are actually things that are satisfying boundary conditions of how you can make a certain current and voltage flow through certain things. So if there's two resistors in series, what you're ensuring is actually that by the voltage drop across those two things, you're ensuring that the total current, let's say in that loop, let's say that there is a resistor here. Let's say there's another resistor here. When you do your calculations, you're ensuring that this current and the voltage drops all allow for the ratio that they equivalently define, if you know what I mean. So you're going to put a voltage here so that the current, we know that the current has to be the same. We'll say this is Vn, and we'll say this is, let's call this not, and we're going to deal with circuit theory. So this we're not going to call Vn, we'll just call this V1 because Vn is actually our source. Let's call this Vs or source, and we'll call that Vn. Vn, which is the voltage across that resistor. There'll also be a voltage here, which we call V0. Okay. What you're actually doing, if you find the current or the voltage or whatever, you can just sort of say immediately that the voltage is equal to Z0 over the sum of them, Rn plus by Z0 times by Vs. That divider rule actually is ensuring that the voltage, this V0, will actually create the current that will go through here. Okay, it will make a current when you divide it. And that will be the same current that if you do the same rule for Vn, which is Rn over Rn plus by Z0 times by Vs, you'll notice that when you divide this current, divide this by Rn, you'll get that both of these will give the same current. You've actually, your equations, all of your sort of calculations were ensuring that you were satisfying the condition of the ratio of voltage and current for each resistor, and that the current in the loop must be the same. That's what your circuit theory was doing. So now going back to transmission lines, we get approached with this. We close the switch, we've closed the switch, and now we have our two terminals, our transmission line. It also enforces a ratio of voltage and current. No signal has traveled down the transmission line, but it's enforcing this thing. So actually, we treat it exactly the same way as a resistor. And now we can actually find an initiated voltage of V0, let's call it. And will equal to what? Oh, no one wrote the reflection coefficients, and now I need someone to write the V0s. Okay, write V0, I'm going to write the reflection coefficient. This one will be Rn, remember, that's for this one. This will be Rn minus Z0 over Rn plus by Z0. Then the one at the load, it's going to the load, so it'll be RL, and it's coming from Z0. We also got a PAPI, as you can hear. Z0 plus by Z0. What is V0's value? Are you guys there? Hey, little pup. Come here. There's all preparations happening here. Does anyone know? Voltage divider. V0 equals to PVS. Okay. So in the steady state condition, before there's a traveling wave, now we're initiating a wave. The sort of same, come here, you little pup. I know you want to go out, but you can't go out. That reflection. Oh my goodness, you little pupper. How can I help you? I can't right now. The V0, now there's no traveling wave. We're saying that it's doing the steady state, okay? Because the actual reflections that are happening are so they are so, yes, there we go. They are so fast that they actually just use normal circuit theory. You'll see that in transmission line theory, you actually get in steady state. So if you let time run out and these reflections go around, so there's going to be a wave that travels. So this is like over here, there'll be a wave that travels here. Some will go to the load, some will come back, some will maybe go back into the source. Will go, some will go to the load, and each time you're compiling this reflection coefficient, which is less than 1, okay, so then this reflection is getting smaller and smaller and smaller and smaller. Eventually you'll get sort of something. If you're to look at your time signal at, like, let's say the input, it will look at something like this. Maybe it'll fluctuate up and down, and what you'll eventually get is a steady state signal that will be circuit theory. Okay, so what we say when we initiate this is that we're not considering transmission line effects because the distances are so small, because it's so close by, that we just immediately have circuit theory. There will probably be little tiny fluctuations, but they're not so significant. We'll say they bounce around so quickly because the distances are so small that we just do normal circuit theory. And that is why exactly V0 is equal to Z0 over Rn plus by Z0 voltage divider times by the voltage. And this will be our initiated wave. Okay, so as that switch is closed, we get an initiated wave of V0. Does that make sense? We get this initiated wave. The reflections are happening so quickly that we're not going to do what we're about to do in this transmission line, because here we're saying that the thing is actually long enough. Okay.
Sir, can I ask a question?
Yes, please.
So I understand how the voltage divider works, but in a circuit where you have the load as well in a steady state circuit, then that load resistance would also be considered in the voltage divider equation. So why is it not considered in the initial wave equation?
Because the equation that you're trying to justify from a circuit theory point of view is making the assumption the logic that you have currently now is that you're under the assumption that reflections don't matter. Because everything's happening so fast. You're actually making the assumption that to make these calculations that we just did right now, that everything's moving so fast. It's not actually what's happening, but it does happen when you let time play out a little bit. The reason why we don't consider this load resistor here is because there's a significant distance between the two of them. There's going to take time for it to travel. In this scenario, our source, the source voltage that's being produced, that's being initiated, does not actually have any knowledge of that resistor yet. It actually has to travel, get to the resistor, reflect back, and then it will reflect back, and then that sort of communication between the two of them will actually make traditional circuit theory. That bouncing around makes that circuit theory. So in this case, we're saying that that bouncing hasn't happened yet, and then that's why we don't actually consider that load resistor. Does that make sense?
So then why don't we just consider a small amount of the Z naught from the line? Like, what if it's 10 meters? Then why do we consider the whole thing for the initial voltage if it's for a very short time?
Well, you see, so Z naught, remember what the definition of Z naught was. Z naught was it's the ratio, but can you see that it's dependent on the per length values, not the total values?
Oh, okay,
So
I think I understand.
we are in fact doing what you're saying, looking at only the very small piece next to it, which is just enforcing voltage to current ratio, which is the exact same thing that a resistor does. Okay, you satisfied?
Yes.
Okay, cool. What happens to the reflection if the terminating impedance is complex? Does it become sinusoidal? Oh, so if the thing is, if it's complex, then I assume you'll probably have some form. You'll get a reflection. It will actually have a similar sort of. I don't actually know. I've never actually seen what happens if it is actually complex. I'm assuming it's going to be some sort of similar thing when you, like in this scenario here, when you have two transmission lines. You'll get a reflection because there'll be some sort of impedance associated with that. And yeah, because these, remember, are actually capacitors, inductors, and capacitors. So it'll probably have come down to something like this. So if it's just a capacitor, maybe that'll be 0 or something. I actually can't answer that straight away for you right now. I think you might. I think it will just do some form of time delay in your signal. So it will charge it. It doesn't necessarily mean it will be sinusoidal though. So it can be like a ramp. It could make something like this in time, like what we saw before, depending on what your input was. If it was a sinusoidal input, then you would have a delayed sinusoid, which is what you see with all the other power things, where you have that sort of, you'll make your like current lag, for example. So where things, maybe the wave fronts were intact, where voltage and current was moving at the same speed together, maybe one of them will lag because voltage will be stored slightly, and then I assume, but don't worry about that from this context now. Let me move on to what happens next. Okay, so we have an initiated voltage. So I'm just going to draw the transmission line, and now we have initiated voltage. This is different to a traveling voltage. because we initiated it, okay, for that reason that everything happened very quickly. We're just not considering those effects, pretty much, because it does seem a bit weird that we'd have one different rule for the initiation, but it is because we're kind of starting it out, and we're saying the other transient effects are not important at this point, because they aren't, because the distances are so small. V naught wave. Okay, so now V naught voltage, and there'll be an associated current. The current will be V naught divided by Z naught. Okay, so this will be a wave. It means that in distance, okay, here it was 0 volts because it was charged, and now we have V naught. And what's actually going to happen is that this wave is going to travel down the line, in the same way that if you were to quickly take a string and move it, let's say you have a string like this, okay, and let's say we take one point of that string and we move it up quickly, let's say instantaneously, like a step. What will actually happen is that will cause all of the things to move up next to it like this, and you'll actually have a moving wavefront that will be a perfect step like this. We don't see this in real life because we get something that will change in some sort of a distance, and there'll also be some sort of like lossy components that will smooth it out. But here we're dealing with lossless, so it can actually be a step. We have a traveling step, a traveling wave, okay, that's going to move down the string. The same thing is happening now on our transmission line. We have V naught moving down the transmission line. Okay, we can actually say in what time period that will happen. So we know, for example, that this will have a certain velocity, which will be the square root of the per length, things like this. We also know that this has a physical length. Okay, so then we could know that length, I think it's length divided by velocity, will give us a type. Is it divide meters per second?
Yes.
Okay, and that will give us a time delay. Okay, so we all know that there'll be a certain time delay for the signal to reach the end. Okay, we can call that delta t. So if we were to graph in time, okay, we'll do this. Okay, let's just draw this on the side here. We're going to draw two graphs. We're going to draw a measure of voltage at the input of the transmission line, and we'll say voltage at the load. Okay, and then we're going to put little sections on it. We're going to say like delta t. We're going to speak about it in terms of how long it takes for a signal to get to the end of the line, and we'll say like 2 delta t, 3 delta t. So in transmission lines, you'll see this a lot. They speak about delta t's because it depends on how fast things move. So that's more important than actual time, because you'll see all your key events happen at these specific times. Okay, so V in, as we start, we'll say at time equals 0, we have V naught. Okay, so now a wave will travel, and then it will reach the load at this time. Okay, the input will have nothing about that. That's like if we look here, we'll have a wave traveling over here. The input will only change when a reflected wave comes back. Okay, so it will take, if we look back here, it will take 1 delta t to move down the line. Then it will take 1 delta t to move back. So now the load actually won't, the input won't change. It will still be V naught. Only now, once it arrives, you'll actually get a reflected wave that will be added on top of this. And the value of that would actually be the reflection coefficient of the load times by V naught. But then you'll see there's actually two reflections happening here. Okay, let's come back to this. We're going to populate this graph, but just to give you an idea that things are taking time. Also, with the load over here, it would be 0 only until it reaches there. Okay, it's going to be 0, and then it's going to step up to a certain value. And that's what we're going to see now with our reflection diagrams, exactly going to show us what that value is going to be. Okay. So let's draw it like this. We're going to use a handy little diagram. Okay, it's going to be called the reflection diagram. So let's just draw what is happening over distance now, not time. This was over time. Here we're going to do it over distance. And if this is our transmission line, like this, we're going to have a wave that is traveling. Okay, so this is from 0, t is greater than 0 or less than delta t. We're going to get something like this. Okay, and then that's going to hit the load. Now, as it hits the load, so here's our load, and it has a value of RL, I think we said. Yeah, you see, it has RL. It's going to hit RL. So we're going to say at t is equal to delta t, there will be a reflection. The reflection is going to have a value, so that the incident wave is V naught. The reflection coefficient is going to be the reflection coefficient that we calculated, which is this, OL. Okay. So this is going to be our reflected wave. This is going to be V naught. This is going to be RL minus where we came from, RL plus where we came from. So you normally calculate this first, so you just refer to it. And this is going to be the value of our reflected wave. Okay. And that's going to travel back towards the source. So now let's say, let's draw the time graph now, I mean the space graph for what's happening now. Okay, so now there's a reflected wave. On the line already, there was V naught. Okay, now what's going to happen is there's going to be an additional wave. That additional wave is going to have a magnitude of V naught. So this first wave had a magnitude of V naught. This one has a magnitude of V naught times by the reflection coefficient. Because now we have a traveling wave. Okay. So this is for delta t less than t less than 2 delta t. Okay. So now we have a wave traveling back. What does that mean? That means that here, so this is the voltage at the load. Okay. And can we see that at the incident that it actually reflected, so this is at t is equal to delta t, when the wave just arrived and it reflected. So that happens, we will say, instantaneously at that moment. It reflects at that instant and adds. That would be just like over here, just as this thing is moving. We have VO. Okay, now the total voltage is going to be equal to V naught that arrived plus by the reflected wave. V naught plus by gamma OL. Okay. So depending, that can be a negative wave. If this value is negative, then that could be negative, and then you would actually get a scenario like this, where not, okay, and then we would have a negative wave, so it's just draw it underneath now, moving like this. And if you add those two waves together, you actually get something that looks like V naught was there, and then V naught minus that wave, because the reflection coefficient. And then that will travel along the thing. So it'll look like this. You'll get something that goes like this to the new value. And then that will travel. And then you'll see that that wavefront is going to reflect now. Okay. So if we see what is the value actually at delta t for the load, okay, because you remember it was 0, then at delta t it steps up to a value. And it actually steps up to a value and will remain there until another reflection comes. So we know at least for one transit period it won't change. And it was actually the value of V naught plus by V naught times by the reflection coefficient of OL from the the line to the load. Okay. So yeah, you can actually be asked to draw these diagrams. In my exam, we were actually asked. I wouldn't just think about it though for online. That's not a main exam sort of question. That's more of like a sup deferred sort of question. The more drawing sort of questions, because there's less people, we can ask harder questions and actually have to be encouraged to ask harder questions. That's where you can expect something like this. I wouldn't say, yeah, you can get asked it really, and it's not actually hard. You'll see now that's not hard. When we actually get to the point of the reflection diagram, now we're in the initial hard phases where we're moving through the mud. Just to get to the point, it's a bit confusing, but you'll see when we actually get to our final structure of the reflection diagram, this stuff is a joke. It's really easy. Okay, so now let's continue. First, is there any questions? Just type them out. I'm going to continue anyway, but just type them because I'm going so far over time. But I think it's useful. So remember, this was for the time after the first reflection. So the first reflection was at delta t, and we know it's going to be less than the second time, because that will happen when this wave reaches here. That will be 2 delta t, because it was 1 delta t there, 1 delta t back. So then that 2 delta t's will be back at the input. Okay, so let's see what happens. We have this wave. Let's draw what's going to happen now. Just at the point where t is equal to 2 delta t. So at t is equal to 2 delta t, what's going to happen is this wave. I should literally actually get my masters out so you guys can check this, because I actually have a really good diagram of this. This wave, okay, which was here, has actually traveled. So it's traveled, and now it's hit another reflection, the impedance mismatch, and it's going to reflect as it did over here and created one reflection. Now this actual traveling wave is going to reflect. So this thing that has traveled now, this is kind of on the line static. It's like kind of almost DC value on the line, but we have a moving waveform of a value of this OL, and we're going to say that it actually at this point has hit the input impedance. Now that wave, let's just move this a little bit down. That wave, the incident wave, is what's going to reflect, not the total voltage on the line. So there's two different concepts: the value of the reflection, the moving wave fronts, and then there's the total voltage on the line, which are two different things which you can be asked. What's going to happen now is that this traveling wave front is going to get reflected. Okay, now again, I'm going to draw it as positive, but it can be negative, and most likely if it's converging to a value, it will be, well, it will always converge to some sort of value. Well, unless it's there's actually cases if it's like an open circuit, you can get like voltage will continuously increase, kind of like charging a capacitor. Yeah, but don't worry. This thing is going to get a reflection. I'm drawing it as positive, but it's very likely that it will be, something can be negative here. So that would actually go underneath like this, you know what I mean? Subtract from it. But now we're just saying it's adding on top just because it's easier to draw. Oh, you see. Okay, so now we're going to create a traveling wave. I'm just going to draw it a bit bigger because it's a bit of a longer value. And it's going to have a value of the incident wave, okay, which is this. Hello, other dog. Oh my goodness. I didn't know you could jump like that. Okay, now it will get a value of, it will get reflected. That instant wave will now get reflected by where it was coming from to the input. So now it will get that value, okay? And then this will travel down the line, okay? Now then this is actually going to get to the load again. So what we'll get, so why I'm drawing this as like they're all adding up. Like they do just add up indefinitely. And they're positive. Well, they do add up indefinitely. But they'll actually be getting smaller and smaller. You'll notice that each time, because these are two things less than 1 times by each other, you get an even thing that's even less than 1. And it gets smaller and smaller and smaller and smaller. You'll see. So actually I've drawn them all as the same height just so it's easy to see. But you'll see they actually get smaller and smaller and smaller. I'm going to get my thing after I've just explained all of this. So let's draw what we had. We had the initial V0 that went to the load. Okay, and that V0 was initiated by that voltage divider because we could deal with circuit theory in that initiation stage. Then we got a reflected wave that reflected back. Then that wave got reflected again. Okay, so this one was the first one that traveled there. Then the one that came back had a reflection of OR. So now this one traveled in this way. Then we had another one, which was V0. This was the initiated wave. Then the wave that had arrived at it, it got reflected, so we times it by a reflection coefficient. This is OL, no, not OL, sorry, OI. And then that's going to travel that way. Now we get to the end again, and this, the arriving wavefront is this, exactly what we had. OL, OI, and now it's going to get another one of these. It's going to reflect, just draw it in green. And it's actually going to travel back. Okay, instead of actually drawing it like that, let's just square it like that. And then that will continue to happen and happen and happen. So this is voltage. This was where we were on our transmission line, the traveling wavefront. Okay. And then, okay, so now we can look over here. We can go back. Let me just show you. Let me get my thing quick. Where is it? Let me just show you. Here we go. So here's sort of a single transmission line. Wait, let's see. Here's the reflection diagrams. Where is the actual one? Well, there's not a diagram. Oh, here we go. So here's a diagram of what is happening. You had V0. So this is a reflection diagram that we're going to get to. I'm going to show you about now. There's a wave traveling. It got reflected. You see, so the value of that wave is shown on top of it. So there we go. I got a reflection here. I call it AB from A to B, and I call the one from B to A, BA. And then here we go. That gets reflected. So you see it gets an additional one. It gets the BA over here. Okay, then that's going to travel. Then it gets another one. So you square it. So that's as far as we've gone. Then you square. So you can kind of track these voltages over time. If this is distance and then this is time, you can actually say, okay, at a time, we can see that there'll be a wavefront at this distance. And then this is the voltage, which I was kind of showing you. So the net result of that is something like this. If you draw it over time, you get this thing that adds and gets smaller and smaller and converges to a value, a steady state value, as I've called it here. This steady state value is actually, if you were to put in the values, what you get if you do normal sort of circuit analysis on the circuit. So there's kind of a scenario where you have a source resistor, exactly what we're doing. We have a load resistor 180, and then we have an impedance in between of this. And then if you just do the voltage division of like the load resistor, which is on the other side, so let's just do this. So you see that this thing, I actually calculated this, and this converged to 7.2 volts. Let's just say that we have this, just so I can show you. Okay, what this scenario looks like is exactly what we're doing now. So we have an 8-volt source like this. It had an input impedance. Did I give it an input impedance? Yeah, of 20 ohms. This was connected to a transmission line of 60 ohms. Okay, and then there's a load of 180 ohms. Okay, and I did literally the rules of there's a traveling wave. So you initiate it first by doing, if we have 20 ohms, and then here we have 60 ohms, what we'll see, and 8 volts, okay, we'll see that our V0 is equal to 8 times by 60 over 80, which will be 10, so it'll be like 6 volts. I think I did that very fast, probably wrong. 6 volts will go, then it will reach the end. Let's see what the reflection coefficient would be. The first reflection coefficient. Okay, let's just call this from A to B. If we label this A and this B, so it's coming from A to B like that. We'll say reflection AB is equal to where it's going, is the load, which is 180, minus where it's coming from, which is the transmission line, which is 60, over 180 plus by 60. That's equal to 120 over 240, which is equal to 0.5. Okay, so then what will happen is that you'll get 3 volts coming back. We'll get 3 volts coming back because we have 6, the initial volts, which is 6, times by 0.5, which will give us 3 volts. Okay, so that means we had that traveling one that came, 6 volts. Then we have a reflected one that came back, 3 volts. So then the total voltage at that time was 9 volts. Okay, so if we go back, if I did that right, you see, okay, so I do that calculation. So then that means at t, you see I use the same sort of notation. This is standard notation. As it arrives, we get 9 volts, the combination of the initiated voltage and the reflected voltage. If you look at the transmission diagram, you can see that the voltage at t is the combination of the initiated voltage plus by this. Can you see at this point it's 2 of those things? And that will become the DC on the line. Okay, well, I haven't even seen if there are any questions. I'm not. Please zoom in. Oh my goodness, sorry, man. Shit. When I changed the window, I couldn't see the chat. So to find the stable value, you have to apply circuit theory. Yeah, so the circuit theory will give you. So when we do this process, so eventually, so that's what I wanted to try show you. If you carry on, oh no, I'm going on the wrong place. If you carry on doing this process of adding up the waves, like what I was showing here, okay, well, if you carry on doing this process where you're adding up all these things, you can see that over here, that there are portions that it was negative, so it's going under and over and under and over, and I get to eventually, can you see it was 7.3, it kind of getting close to 7.2. If you go back here, and we actually do this scenario here that I was showing you, where there's a 20 ohm, a 180 ohm, and let's just draw it as we don't consider the transmission line. Let's say it's all the reflections have happened. Let's just do normal circuit. So this was the initiation, just don't get confused. This is for initiation. Now we're going to draw the circuit. Let's look. Do circuit theory, this is 20 ohms. If we do this, this is 180 ohms. Okay. What's cool is that, look, let's find what is actually the voltage. Let's do normal circuit theory. What is the voltage? Okay. You get 8 volts times by 180 over 200. So that's 180 plus by 20. And if I just do that on my calculator quick, 180 divided by 180 divided by 200 times by 8, we get 7.2 volts. This is what this thing does. It's basically saying each time this thing reflects, it's enforcing its sort of condition. And basically what's happening is that the source resistors are enforcing a condition. The source and the load are both enforcing this condition. They're both kind of communicating to each other what they want. And it will travel. Okay, it says, no, I can't do that. So it does a reflection. That's what's the excess energy, the reflection. It reflects. You add. Then that is actually where they both agree. Circuit theory is the point where everyone's agreeing. It hasn't gone through the process of fluctuating between not agreeing because they're not actually directly connected. It takes time for them to actually communicate, for the mismatch to kind of to settle. And this is how it settles. This is what the whole point of transmission line theory is, to show this sort of settling procedure. So the final thing that I want to show is this diagram. If we just draw this basic circuit again very quickly, I have to do it quickly like this, and I'm going to just extend it like this. Okay, let's just zoom in a bit. We can draw this amazing thing called a reflection diagram. Okay, let's just make this a bit bigger. Oh my goodness, just erase everything. Shame, everyone's probably thinking, what is going on? Why are we taking so long? So I'm just trying to go a bit faster. Like this. What we can actually do is draw this thing called a reflection diagram. I like to draw it down like this. You can draw it with this vertical axis pointing up. I like to point it down. We're going to label this X. We're going to label this time. Okay. We're going to say, okay, we're just going to label this one what we were labeling it before, OL, the reflection coefficient when it arrives here, the reflection coefficient when it arrives here, OI. Let's say we have an initiated voltage that we did by that divider. It takes time, V0. So we know that actually the gradient of this line is related to the velocity. So the more flat it is, it will actually be faster, because that means that less time is traveled. If you see from here to here, if you make this smaller, then that means that your delta time is smaller, so your velocity is faster to do a certain distance. Okay, so we can also say that at this point, this was delta t. Okay, we'll say that the wave gets reflected back. Okay, that wave is going to be called, it's going to have a magnitude of this. Okay, now it's going to arrive at the resistor, this input resistor RS. Okay, and it's going to go back. Okay, we know that this time is 2 delta t, because you see 1 delta t has traveled. Each distance that it gets takes a delta t. Here, it's going to get the thing that initiated it. You write it first. This is what has initiated it. It was this thing before it initiated it. As in the previous case where V0 initiated it, we wrote just V0. Now we have a case where V0 and the load reflection coefficient initiated it. So we write that whole thing. Okay, and now it gets an additional reflection coefficient because it's reflecting back, and this becomes that. Okay, now then that wave, which will be smaller than any of the waves before because it will be some reflection coefficient which is less than 1, will now go back. And what will the value? We write down what we had first. What we had that was there was this. This is what initiated it. Initiated the reflection. However, it got another term, you times it by another one of this, so we just square it. And then that keeps on going on and on and on. And then we actually converge. You'll see it's an infinite sum of a smaller sum, and then that's a convergent series, actually. And if we were to graph this, so now what's amazing about this diagram, okay, is that we have on one axis distance and we have one axis time. So we can ask ourselves, let's say let's say, for example, I'm going to draw this vertical purple line, this horizontal, sorry. This is going to be our time investigation line, okay? And we can say at time equals, let's say, less than delta t. Okay, let's just put it here. We can see, we can investigate, so this is like less than delta t, we'll say whatever proportion of delta t, whereas delta t is your transit time, how long it takes to get to the end. We can see that there, at this time, on the line, we can see that everything above it, that means that that exists on the line, okay? So if we're to draw what is actually on that line in our transmission line over here, that means that up to here, there's actually a voltage of V naught. And then you can see that above this line over here, there's nothing there yet. So on this side, it's 0. Okay, so that's what's actually happening. We can investigate it. We can see at that time, that's spatially where that thing would be. Let's go, let's just, can I go Control Z? I can. Let's just move this thing down. Let's move it down. I'm probably going to move a lot of stuff with it. Let's just move it over here. Let's move it over here. Okay. Some time over here. So we can mark our key point over here. We have one traveling wavefront over here, and this is at a time. Okay, so we're investigating a time. We can actually see that we'll have some sort of wave of a certain magnitude at this point, and there will be actually a wave on the other side. We don't know the size of it. Let's say it's less. We're just going to assume it's less. But how you calculate it is that for this portion that I'm going to label A, okay, this portion that I'm going to label A is this part. Okay, this is A. And you'll see that it has A is equal to V naught plus by V naught times by one of those loads. And we'll say that it's also plus by V naught OL OI. So that will be the value. If you add all of those together, that gives you the magnitude here. And then you'll see that to the right of that, let's call that B. Well, let's not use purple or whatever. Such a mess now anyway. To B, it will be all the same things, except it's not going to include this most recent reflection. So it'll be everything. It'll just be everything but one less than this. This just not including this. So then the height between this will just be the traveling wave, which is what we expect, because that is actually the traveling wave at this point. It's the height of that traveling wave. So that's what the reflection diagram tells you. You can also, in a different way, let's just draw it again, so you know what it means. Let's just draw it again quickly. So you see how simple this thing is. Maybe it doesn't feel simple, but if you actually just see that your procedure is drawing lines and giving them labels and giving them a reflection coefficient when they arrive at a certain reflecting condition, it's very simple. So if we have this sort of scenario again, this is just with the single transmission line. You can get 2 transmission lines, and I'll show you what that would look like. What we can also do is we can investigate at a certain position. As over there we're investigating at a certain time, we're going to investigate at a certain position. And what we're going to investigate is actually the voltage, the time wave. Here we had the positional wave over here. Here we're going to do the time wave. So let's just draw it. You see, I'm not going to draw it actually. You can draw it vertical, but I'm not going to draw it vertical. So here's time. I'm going to say this will be VL. So you see, if we say X is equal to the length, then we're looking at the voltage at the length. Let's just mark off all the key points. Okay, so we have one point here. This is delta T. So let's mark all the intersections. This is, so here this would be 2 delta T. This would be 3 delta T. Okay, so that's when changes are actually happening, when reflections arrive. We'll see, okay, let's draw the values. This is V naught, This is V naught. We'll just say gamma load. I'm just going to call it load because there's only one transmission line. This will be V naught, gamma load, gamma source. So obviously this is the reflection for the source. This is a reflection for the load. And what we'll see is that if we mark this as delta t's, so you'll speak about delta t's because that's when your events are happening. We'll say 3 delta t. And what we notice here is that actually every second delta t there's a change. That's because, come on, why aren't you clicking? Imagine, I could erase. Imagine. What's going on? Can I just delete it then? There we go. Okay, and then we'll call this 4 delta t. What you'll see is that, okay, when was our first event? Okay, that's delta t. What is its value? Okay, we can see that it's V naught and V naught L. So then we'll know that the height at delta t is going to have a height of V naught plus by V naught gamma L. It's very small. V naught plus by V naught gamma L. Okay, and then that was actually going to stay the same until our next event. Our next event is at 3 delta t. So here's 3 delta t, and we'll say that nothing's changed because no traveling wave fronts have hit this thing, so it's going to stay like this. Okay, then at 3 delta t, it's going to have a certain value. Let's see what that value is. Okay, let's see all the wave fronts that were on the line. So we look at everything that was on the line. You could see what's new. So what's new is these two. Okay, so then that would represent this. Or you can see the total thing. Okay, you could see all of them, which was including these previous two. But those previous two was what was here. So basically all we need to consider is the new two. So that would be everything that what it was. Okay, so it would be V naught plus by V naught gamma L, and I'll plus by the two new ones, which is this one here, and then we'll just draw another one, V naught L squared Vs, and that will be plus by V naught gamma L plus by, oh, this is gamma S, plus by V naught gamma L squared gamma S, and then that will be the height, the total height, if you include this green part over here. This green part is this part, and then the orange part is that orange part. That's exact. So you can investigate this thing in space or time. You could even investigate it at some distance over here, and then you could mark all your key points. Here's a key point, here's a key point, here's a key point, here a key point. And then you could find out what is the time of those key points. You're not going to go into this depth, but this is what's possible with this diagram. You would at most look at what's at the load and what's at the input. What is happening? What is the value of the reflected wave? So I could say there's a diagram, you draw it out, there's a thing over here, there's a thing over here, there's a thing over here, there's a thing over here. You know how to label these, 1, 2, 3, 4. You'll know how to label those because you just follow the procedure. I can say, let's say a time is equal to 3 delta t. I can ask you, what is the total voltage at the line, on the line? Okay, and I can ask you, what is the total voltage on the line at the input of the line? Or I could ask you, what is at the load of the line? And then that would mean, okay, so either you're going to say, so at 3 delta t, so if this is 1 delta t, this is 2 delta t, here would be 3 delta t over here. I would say, what is the total voltage at the line? Let's see at the input. Okay, at the inputs over here, we're dealing with over here. What we can see is that this wavefront, we're looking at everything above it. We can see that this wavefront has already hit it over here, this traveling wavefront. So we would know that the total voltage at the line at the input, we'll say VNT, and we'll say that 3 delta t, is equal to will be this first one will be underlined, the second one will be underlined, the third one will be underlined. So it'll be the voltages of 1 plus by 2 plus by 3. Okay. If we say for the source, we'll say V, not source, we'll say V load total at 3 delta T. Okay. So this is right at here. V load total at 3 delta T. Let's look at it. Okay, so that's over here at the load. We can see that, look, actually at this point at 3 delta T is actually the point where a new one is made. A new reflection is made. Okay, of value 4. So we would know that actually the voltage would be 1 plus by 2 plus by 3 plus by 4. So what we can see is that the difference between these two things is that the one has the 4 and the one doesn't. Okay, the load has the 4 because actually that's just as a wave hit it, but that will only actually reflect at the input at 4 delta T when it arrives over here. But the load is aware of this at that time. So this is the beauty of this diagram. But can you see the actual procedure is simple? So you can ask, okay, well, at 3 delta T at the load, I could ask you, what is the value of the reflected wave at that time? Because we can see that there's one reflected wave at that time. And then the value would be value of 4. The value that you calculate over here. And that's about it. That is, in summary, that is by far more complicated than it gets, yeah, that you get. Yes, question.
So I'm still a bit confused. So do you mind going back to the example that you just did with the equivalent circuit and the bounce diagram?
This one.
No, with the bounce diagram. Yeah, that one.
Oh, this new one with all these labels, yeah.
So I'm a bit confused as to which parts of what we're adding to the wave. So the first generated wave is the input voltage part of the multiplied by the voltage divider equation, which I understand. And then when it goes to the load, is the number 2 there, the reflected one, the rho times that voltage? And isn't there another wave that then goes through the load that's the original voltage plus rho times the original voltage?
So, okay, so if we're dealing with a transmission line, we'll have a traveling wave. So, okay, good, very good question. We dealt with a resistor, okay? Now, a resistor is something that is a load. It signifies a dissipation of energy. So that there's a transmitted wave, actually, there is in fact a transmitted wave. But that transmitted wave is actually what's absorbed by the load.
Okay.
So that's the energy you actually supply to the load. So when you do two cascaded lines is what they call, instead of it being absorbed by the load, you actually can track it. So let me show you what that would look like. And in your notes, you might see something like that. So this is like this sort of scenario where we have two transmission lines of two different impedances, okay? And here we have a variety. So here's where it's very important that you understand your reflection coefficients labeling. We have, you see, so we have AB, which is going from A to B. Okay, so it's going from A to B. What did I say? Yeah, so then that means it's going to Z1. See Z1, Z1, coming from Z0, Z0, and then the sum. So there we go. And this is going back. This is from B to A. So if you're going from B to A, you have all these different ones. So you need to know the difference between all of those things. But if you actually draw the diagram for that, this transmitted waveform, okay, so there's a transmission coefficient, but I'm not so sure how in depth you guys go into these dual sort of transmission lines. But actually the transmission coefficient is actually 1 plus by your reflection coefficient, because basically what you say is that the total voltage at this line with the reflection is what gets transmitted. So you actually add these two together, which is the same as saying 1 plus by the reflection coefficient. times by what was the incident wave. And then that gets transmitted through. So what you're saying, okay, where's the other reflections? If it's a resistor, there isn't. This amount is actually absorbed by the resistor. And then you just deal with this. But then you see in this more complicated scenario, you get one that actually will get to the end of the load, which will be something that's based on these values of Z1 and RL. And then that will get reflected back. And then at this, one will get reflected back and one will go through.
And at your 4 tau there, is that impedance matching? Is that why there's no reflection?
Yes, exactly. So why there's no reflections coming back on this side is because the impedance is matched. Perfect.
So I just have one more question.
Yes.
So in your examples, I think that you're referring to the top half of the equivalent circuit every time, that like the first, when it goes from positive to the resistor.
What do you mean?
So like if you just go up a bit, scroll up a bit there, or a little bit, yeah, you could say that.
Yeah.
So that one of the 8 volts, that circuit, I don't know if I'm understanding it correctly. I'm imagining that you're just going like from the 8 volts, if the positive is north, then you're just going 8 volts to the through the 20 ohms, then through the A to B, then it hits the 180 ohm resistor, and then it goes back, and you're not talking about the current going through the 60 ohms at the bottom.
Okay. Fantastic. Very, very, very fantastic observation that. So again, so now this is where you are now. You're dealing with what you've been showed in circuits so far is voltages and currents. And it's very good. You're trying to understand this thing from what you know. And you're like, okay, well, what's going on here? We deal with these circulating currents and whatever. So perfect. Good. I'm very happy that you're analyzing this. You're really thinking well. However, we're in the world of traveling waves. In traveling waves, we actually look at electric and magnetic fields. So to make that point, okay, let's say we have 2 conductors, and you'll see that this whole concept of, like, I don't know if you remember doing twisted pairs, where you actually couple 2 wires together. This is a similar sort of thing. When we say a voltage is traveling, remember a voltage is a distance in an electric field. Okay, there's an electric field between these 2 lines that is actually traveling. That maybe makes more sense to think about as an electric field traveling between these 2 lines. And there's a wavefront at which it's traveling from, this electric field. You could say, because we know the distance, that this is actually a voltage front that's moving. Now, when we have an electric fields going like this, and then at right angles, you have like sort of magnetic fields that move like this. What actually ends up happening is that, remember, if you have, for example, a current, you get a magnetic field around it, like this. If you have a magnetic field, you kind of get a current around it, in a way. They're kind of vice versa of each other. So what happens is that when you have these electromagnetic waves, remember that they're both together and they're actually transverse waves. So in this sort of right angle sort of configuration that we have here, that's one of the assumptions, but we're not really speaking about that because you don't actually know anything else, but it's fine. If we have these magnetic fields like this, what ends up happening is that we get a circulation of current. Okay, so what that means is that we have a current going like this, sending and returning. So as a voltage is traveling like this, you actually get these electrons immediately opposite each other communicating like this. So where you'll get compression moving forward of the electrons, or dispersion moving apart, which associates to things moving into the gap, you get a circulation of current. So that's why you don't actually need to, where you're looking at it as going like this, which is what you're used to with our analysis, that's not actually what's happening. What's actually happening is that there's a traveling wave and there's a current that's over here that's directly related to the current underneath it. So your transits, when you say you go through like this, it's actually interacting with both sides. So your path of travel in a circuit, let me just draw the circuit again. In the circuit like this, I just ignored the one resistor, even though it should probably be there. The path of travel with electric fields, remember it's between both of these things, like this, is actually like this, forward and back, like that. And then that's why in our diagram, we draw it only one to there and back. We don't need to have an additional movement for underneath. They happen simultaneously.
Oh, that's cool. Thank you.
So yeah, circulation, it comes back down to Maxwell. These things are amazing. If you think of things like these with these curls and stuff, you'll see you do all maths with Stokes theorem and all this stuff. This is actually what it's really, really all about. So yeah, think about fields. Try starting to think about fields, traveling waves. But yeah, if you just look at it as a conceptual mechanical thing that you're going to do, it literally becomes like this. It's like gamma B, then the next one becomes gamma AB, and then you just sum them up. So yeah. Yeah, the lecture videos are good. There is a section in the green book. I forget exactly what section it is. There is one somewhere. I'm not sure if anyone knows, but I remember it being a bit tricky-ish, the green book. So yeah, check it out. It's nice because they speak about things more in terms of like Maxwell and stuff, and way more deep in a way. But yeah, I think lecture videos are a good way to go. There's lots of resources on this online. Again, my master's with the appendix, I tried to make it simple. It's like my sort of goal for that appendix was to explain the procedure. So again, that might help out for derivations if you have questions. But yeah, I think that's really the depth that we went here is more than I think is what is expected of you. But yeah, those are all the basic concepts. Now, if you were to watch those videos again, I think you'd be in a bit of a better way. You're probably feeling a bit lost now. There's definitely work to be done. I'm sure, because I just went sped on, and I sped on because it was taking so long, and I just didn't want to keep you guys for so long. But now I think you're in a better scenario to actually go. When you read that material again, it won't seem completely like lost on you. But yeah, so there's the rough and sort of crazy introduction. Remember that your parameters are all related to these sort of things, which are related to your sort of time derivatives. And because it's an infinitesimal, you kind of get a speed which is associated to that. The wave equation describes that. Yeah, these are per length values. I could tell you that the length of a line is a certain distance. I could say the total capacitance of the line is a certain distance. And then if you want to actually calculate things like the velocity or the impedance, you have to divide it. So I could say capacitance is 500 farads, something ridiculous, and the distance is 2 kilometers. When you actually do these equations, you have to divide the two because you need to find the unit of it. And then SI units as well, with like meters. But yeah, there we go. So there we go. And yeah, just remember that the difference between the conductance, if it's in Siemens or ohms. So you want it infinity ohms for this parallel one because you don't actually want current to go through this. You don't want that for it to be lossless. It's a loss of energy. You want that to actually be an open circuit. But if they say Siemens, then it must go to zero. Same stuff. Is it possible to have a cursor